right, so let's go ahead and move on here. We're going to go and move on to the second derivative test for local extrema. So again, we talked about the local extrema. To find local extrema, we are going to find the f prime, set it equal to 0, and then find where it changes signs, right? Changing of sign is what we're looking for, okay? Where f prime goes from positive to negative or negative to positive. That was our first way. The second way, I told you there were two different ways, two different tests. The second test is when we use the concavity test, okay? So if I have a local max, it makes sense that my f prime is going to be equal to 0, but might also make sense that f double prime would have to be negative, right? You're going to have to be concave down, right? You're going to have to be concave down. So in other words, so to have a maximum, a local maximum, my f prime has to be 0 and double prime has to be less than 0. To have a local min would be the exact opposite, right? I'm going to have a situation where I have f prime is equal to 0 at this point, but also I'm going to be concave up. So f prime is equal to 0 and f double prime is greater than 0. Okay, so this is the second derivative test that we can use to find local max and local min. Okay, if you go to top of page 217, that is written down there. 217, it says if f prime is equal to 0 and double prime is less than 0, then you have a local max. If f prime is equal to 0 and f double prime is greater than 0, then you have a local min. Okay, so let's see if we can use that and do this in example number 6. Example number 6. Okay, realize that I skipped example 5 here, and I didn't skip it because it's not important. It is pretty important, but it's also something that I'm very confident you guys can read and understand, right? So let's go to example number 6. Finding local extreme values of f of x is equal to x cubed, the same function that we had before. So f prime of x, again, is going to be equal to 3x squared minus 12, which means that if I set this equal to 0, I get 3x squared is equal to 12, x squared is equal to 4. So this is going to happen at x equals to plus or minus 0. So I know at plus or minus 2, I'm going to get 0. So what I need to find is what f double prime is. F double prime is going to be equal to the derivative of this, which is going to be 6x. So at x equals 2 when f prime is equal to 0. So in other words, f prime of 2 is equal to 0. F double prime of 2 is going to be 12, which means that it's greater than 0. In other words, it is concave up. So here I'm going to have a local min, right? And the value of that is nothing more than f of 2, right? You can just go ahead and plug 2 in here and find out what it is. And then secondly, at x equals negative 2, again, I have f prime is equal to 0. F double prime of 2 is what? What is f double prime of, oh, I'm sorry, not 2, negative 2, right? We're talking about negative 2 here. So at negative 2, I'm going to get negative 12, which means that I am concave down, so I'm going to have a local max here. Okay, so it's a little simpler because I don't have to look at changing of signs and stuff like that. It's a little simpler there. Okay, let's see if we can do example number 7. Example number 6 and number 7, that f, so in example number 7, I am given that f prime of x is equal to 4x cubed minus 12x squared. Okay, so I need to find what? And we're going to find the extrema, where extrema occurs. So f prime is equal to 0 where? When this is equal to 0, so this would be 4x squared. pull the 4x squared out, I get x minus 3. So I'm going to get x equals to 0 or 3. F double prime of x is equal to what? F double prime of x is going to be equal to 12x squared. 12x squared minus 24x. So I'm going to get what? 12x, x minus 2. This equals 0 or 2. That's really not what I need to know. I need to know f double prime of 0 is equal to what? 0. F double prime of 3, when I put 3 in here, what do I get? I get 9 times 12 is 108 minus 3, this is 72, which is going to be 36. It's greater than 0. So at f of 3, when x equals to 3, I get this is equal to 0 and I have positive, so I'm concave up. So I'm going to have a local min at x equals 3, right? At x equals 0, what's happening at x equals 0? At x equals 0, problem is I have, this is 0, which is good, but this is 0 also, which means what? I am at an inflection point, right? So what do we have here? There's no extreme when x equals 0 because f of x is, f double prime is also 0 also. Okay, so I'm decreasing this. So one of those, I'm getting this kind of thing here, right? I'm getting a kind of thing where I'm going like this. So there's no local max or local min there. X equals 3, I have a local min. So go with that. B, find the intervals on which f is increasing, intervals on which f is decreasing. So to find where f is increasing or decreasing, I have to look at f prime. That's this function here. This function is going to be equal to, so this guy here, if I look at the positivity or negativity here, this is always going to be positive, right? So I'm going to be positive when this is positive, I'm going to be negative when this is negative, right? So at x equals increasing or decreasing, so when x is greater than 3, I have what? When x is greater than 3, this is B. When x is greater than 3, I have this is going to be greater than 0, this is greater than 0, so that means that f prime is going to be greater than 0, so I'm going to be increasing. Okay, when x is less than 3, f prime is going to be equal to less than 0, so I'm going to be decreasing. Again, x equals 0 is a point of concern here, but since the sign doesn't change at x equals 0, I am still decreasing, okay? All right, so we're good there, we are good. Okay, and then C, find where the graph of f is concave up and concave down. Okay, so in C, find where it's concave up or concave down. I would find f double prime, right? I have to find where f double prime. So f double prime, I already did, didn't I? F double prime was equal to 12x squared minus 24x, 12x, x minus 2. So if I graph this, I'm going to get zero and 12. So this is f double prime. F double prime goes, so I am what? F double prime. So when I'm, f double prime is greater than 0, which is over here and over here, I am concave up because f double prime is greater than 0. Here I am concave down. From 0 to 12, I am concave down because it is negative, right? Okay, D, sketch a possible graph for that. And the possible graph is going to look like what? So I'm concave up between 0 and 12. So, and also I have f double prime is here, so I have 0, And I had 0, and what was the other one? 3, right, at 3. So we're going to have a local, this is a local min, I believe. So it was a local min. And here I'm going to have one of these things. So it's going to look like this, it looks like. Yep. Okay. All right. So we're good there. So the last one, example number 8. Example number 8, we're going to actually talk about, this is pretty interesting stuff. This is kind of it's not the easiest stuff in the world. We're going to talk about analyzing discontinuous derivatives. Okay. So example number 8, I would consider this to be fairly complicated. So if I had a function f is continuous on the interval 0, -4 to 4, and the discontinuous function f prime, which is shown on F figure 5.32. So 5.32, we have a graph that looks like this. So this is your f prime here, right? This is your f prime. So from this, we need to find our f, right? So f, so this is going to be, this is 2 and 4, 2 and 4. This guy was 1 and -1 and -3. And this way was going to be -4. Okay, so this is f prime. So f prime, when f prime is equal to 0, I'm going to have so I'm going to go from positive to negative, right? Positive to negative. So I'm going from positive to negative. So I'm going to have a local max here, local min here, because I'm going from negative to positive. From here, again, I'm going negative to positive. So I'm going to have a local min here again, right? So this guy is going to look like what? This guy is going to look like, let's see if I can use this. So there's going to be a line here, right? Because I have a constant f prime. So I have a negative. So it's a line, but it's with a negative slope. Negative slope. I'm going to have an x squared thing here going on here. So it's going to look like this, really. I'm going to have an x squared thing going on here. Then I'm going to have a negative x. It's continuous, right? And then here, looks like I'm going to have something that looks like this. Okay, all right, because I have local max here at -3. I'm going to have a local min here at -1. Okay, that's the min there. Again, I'm going to have a min here at 1, right? But since the derivative is a linear here, which means that the original function is going to be a parabola, right? So it'll be a parabola like that, because I have the f prime is equal to 0 point right here, which means the vertex is actually going to be in here between 0 and 2. 0 and this is going to be 2. Right? And here I have a negative slope, so it's going to look like that. Okay, so this is fairly tough. The reason why I drew an a cubic function here was because my derivative is a parabola. Since the derivative is a parabola, that means that the original function had to be a cubic function that looks like here, with the max and the min actually in there, right? Okay, so that's what it's going to look like. All right, and with that, we are done with 5.3. And like I said before, okay, 5.3 is a fairly important section, okay?